Hi, Dr. Revis here. In this video, I will show you how to predict products from ions based upon balancing the charges and counting the number of atoms. Elements on the periodic table are organized in groups 1 through 18. Based upon where they are on the periodic table, we can make a prediction about what type of ions will be formed. Shown here are the most common ions for the groups located on the periodic table. In this video, we will not be discussing transition elements. We note that group 1, 2, 13, and 14 form positive ions, noted here in red, and group 15, 16, and 17 form negative ions, noted here in green. For the positive ions that undergo oxidation, we have a +1, a +2, a +3, and a +4. For the negative ions that undergo reduction, we have -1, -2, and -3. These are the most common ions encountered. So let's start to build compounds based upon their ionic charge. Let's do it by using some examples. This example shows aluminum, which has a +3 because it's located in group 13, and oxygen, which has a -2 because it's located in group 16. So here's the question. How many aluminum +3 ions and oxygen -2 ions must be stacked to equal the same size charges on both sides of the molecule? In other words, let's balance the plus charges and the minus charges. The plus charges are located on the left side of a compound. The negative charges are located on the right side of a compound. Our goal is to stack enough aluminum +3 ions and oxygen -2 ions to achieve a balanced charge. And here's how we do it. Here we add one aluminum and one oxygen atom, and the balance is +3 and -2, not equal yet. We add a second aluminum and a second oxygen, we get a +6 and a -4. The magnitude of the charges are not equal yet until we add a third oxygen, which gives us a +6 and a -6, which allows us to achieve electronic neutrality in the compound. Therefore, if we take a tally, we achieve this by stacking 2 aluminum atoms and 3 oxygen atoms, and we write that as aluminum subscript 2, oxygen subscript 3 for aluminum oxide. Let's take a look at doing this with barium and phosphorus. Barium, located in group 2, has a +2 charge. Phosphorus, located in group 15, has a -3. Our goal is to achieve the same magnitude charges on the positive side and on the negative side. We start to stack. We have one barium, one phosphorus, giving us a +2 and a -3, not the same magnitude yet. So we add another barium, another phosphorus, and in order to achieve the same magnitude charges, we add one more barium, and if we take a tally, we have 3 bariums and 2 phosphorus for barium phosphide. Let's do the same thing for sodium and sulfur. And now that you understand the process, let's just do it. So, what do? We add sodium +1 and sulfur -2. You know the process now. So, we find we have to stack 2 sodiums and 1 sulfur to achieve the same size of the opposite charges. If we take a tally, it required 2 sodiums and 1 sulfur for sodium sulfide. We can do likewise with magnesium and oxygen. What we discover, we only need 1 atom of magnesium and 1 atom of oxygen to achieve electronic neutrality. Same size, same magnitude of charges of opposite sign, plus and minus. And that means we have 1 magnesium and 1 oxygen for MgO. And here we show you what happens if we do the same thing with gallium and chloride. We find that it only takes 1 gallium of a +3 to react with 3 chlorines of a -1 to give us gallium chloride. In a likewise fashion, carbon, which is located in group 14, and bromine in group 17, -1 for bromine and +4 for carbon. If we stack the atoms to achieve the same magnitude of the charges but with opposite signs, we find that it takes 1 carbon and 4 bromines to give us carbon tetrabromide. So what about the polyatomics? The process is exactly the same. If we combine beryllium with nitrate, beryllium with a +4 located in group 13, and nitrate, which is a polyatomic, we find that if we stack the first group, we do not achieve electronic neutrality. We add the second group, and indeed we do attain neutrality, same size, same magnitude of the charges, but with opposite signs. If we take a tally, we have 1 beryllium and 2 nitrates for beryllium nitrate. We could do the same thing if we react aluminum with carbonate, carbonate being a polyatomic, and aluminum located in group 13. We find that it would take 2 aluminums to react with 3 carbonates to give us aluminum carbonate. And there you have it, a simple way of using charge balance and atom counting to predict compounds.